I just spent the better part of a couple of hours getting a lot of data for pendulum length, period versus pendulum length. Used a lap timer, an online lap timer, and measured first a pendulum. The length was 95.6 centimeters. Now there's actually a plus or minus maybe 0.2 centimeters on all of these measurements. But I measured them pretty carefully with a pretty accurate meter stick. Okay, I measured alternate cycles. And the way I measured this, the pendulum went from here to here and back. And I spotted a point that I thought was very near the middle of the distribution, or very near the middle of the swing. And I tried to time the timer so I would click just as the pendulum crossed that point. Now the reasons for that, the pendulum is moving fastest at that point, so it's easiest to see as precisely as possible when it passes that point. You might think about that and think about whether that's even true. Okay, I measured every other time the pendulum passed the point. So I'd measure click, click. And not every other time it passed the point, every other time it passed the point going in the same direction. So in other words, I measured every other cycle of the pendulum. And here were the numbers I got. Now there's a question, and don't worry about these little tick marks. They don't mean negatives, obviously. It didn't take a negative amount of time for the pendulum to complete its cycle. But these little tick marks were just helpful when I was trying to enumerate the various, well, I was trying to make a frequency distribution. And I got one just to see if that distribution might be normal or not. I would kind of expect that if I continued this for a long time, if I didn't succumb to mental fatigue and start messing up the clicks, start getting more deviation in my times, that the result would be pretty much normally distributed. Of course, that assumes that I'm normal, okay, in the mathematical sense, that my brain wiring and my neurological responses are such that my responses follow a normal distribution, that my errors follow a normal distribution. And I'm unable to verify that with just a couple of minutes worth of data. I would need hundreds of data points. And again, that would have to be hundreds of data points taken without succumbing to some sort of fatigue, and that would be challenging. Okay, 10 minutes I think I could do it. An hour I'm pretty sure I couldn't. Okay, anyhow, measuring alternate cycles, I got these results. And the results appear to range from, I think, about 3.80 to 4.08. I don't think I have any in the 3.7s. Taking the mean, I find the mean is 3.928. I then calculate the standard deviation, assuming these times are normally distributed. The standard deviation gives me a significant estimate of my typical uncertainty in measuring these times, because I want to know just how certain my results are. Okay, so I got a standard deviation of 0.077. Now we know how to do the standard deviation. We simply find the mean of the deviations, calculate all the deviations, square them all, and find the square root of the mean squared deviations. Since there are fewer than 30 numbers here, we actually subtract by one less, or divide by one less than how many observations we have, and that's just a little technicality. It doesn't detract from the general idea of the standard deviation. It just makes it a little more consistent with the normal curve. Okay, well, we have this mean and the standard deviation. That's for 2 cycles. If we divide this in half, we get 1.96 second period, and plus or minus half of that standard deviation, plus or minus 0.4 seconds. Okay, well, I want to do a graph of the period in seconds versus the length in centimeters. This is about 96 centimeters, and that's just coincidental. I just hung the thing up there and measured it. Came out real close to 96 centimeters. 96 is convenient because I can divide that in half, divide that in half, and then I can divide that in half, and divide that in half, and divide that in half before I ever get fractions. Now, I only had to divide this in half once, twice, to get the range of lengths that went from 25.8 centimeters up to 95.6 centimeters. So I've got a pretty good scale here. I didn't use compass and straight edge to subdivide this interval, so this is an approximate hand-sketched graph. I did get some results, and they're posted on the accompanying web page. Using Excel, I got some pretty nice looking graphs. Would have rather used a real mathematical piece of software, but that's what I have available to me here. I can plot this period, plus or minus 0.4 seconds, versus this length. Okay, that the 95.6 centimeters is just a little smidgen to the left of 96. And of course, I'm not able to draw a perfect vertical line here. Even if I constructed it with a compass and straight edge, I don't know that that little bit of deviation would matter, but I put it in here anyway. And I've got the time scale in seconds, and I neglected to write my numbers, but this is 2 seconds, this is 1 second, this is 1.5 seconds. Let's put a little border there. Okay? Now, so here's where I think 1.96 seconds would be. Here's where I think 95.6 centimeters would be, giving us this point on the graph. Now, if I want to really do the graph accurately and to depict the 0.04 second plus or minus uncertainty and just exactly what that period might be, and that uncertainty would really be quite a bit less than that. You go to the uncertainty in the distribution, and you get to divide that by the square root of the number of observations. You get more like 0.01 second, but I left it this way, kind of overestimating the uncertainty. And I can kind of indicate that, and I'm kind of in the way here, using the word kind of a whole lot, kind of too much. Okay, I put a little vertical red line here to indicate the mean, and then 0.04 seconds greater and 0.04 seconds less than the mean. Now actually that little line is too long. It's probably more like 0.06 seconds above and below, but I wanted to make it big enough that you could see it. So there's a little line there that actually indicates the range of possible actual periods corresponding to this length. Okay, well, I did the same thing with a 51 centimeter pendulum, measuring every other cycle. Got a mean and a standard deviation, cut that mean in half, cut that standard deviation in half, and plotted the corresponding point. And I'll go ahead and put a little, this actually is something we call an error bar, a bar that indicates about how much uncertainty we think we have. Then I had to measure every 4th cycle of the 25.8 centimeter pendulum. And I got these results. I didn't want to be timing something as short as a second because I would have gotten well, statistically it works out better if I do every 4 cycles. Okay, just to the inherent uncertainty in clicking the mouse and so forth. So I got a mean of 4.083 seconds, standard deviation of 0.064. Dividing these by 4, since I was measuring every 4th cycle, I get a period of about 1.02 seconds plus or minus 0.016 seconds. Now that's going to give me a pretty short error bar here on this data point. So you see how we could use a large number of timings, not a large number, but a significant number of timings to get a reasonable set of data to use to then predict the behavior of the pendulum and actually to determine the Y factor for this phenomenon, assuming, of course, that this is a power function, and that's just an assumption that we want to test. So we're going to go on with that test in a minute.